Even though the operating principle of proton and carbon NMR spectroscopy is pretty much the same, there are several important differences between proton and carbon NMR spectroscopy. The first difference lies in the operating frequency. As we've seen, that the frequency is related to the strength of a magnetic field, but also the gyromagnetic ratio. The gyromagnetic ratio of carbon is 4 times smaller than it is for proton, which means that if for carbon or for proton NMR we have a frequency of 400 MHz, which is fairly common, for carbon we will have a frequency of just 100 MHz. The second issue is that of sensitivity. We already covered this. It is about 400 times lower for carbon-13, and this is caused by low natural abundance of this isotope as well as by the gyromagnetic ratio, which is lower. Third issue is that of peak areas. If you remember, in proton NMR we use peak areas to determine the number of protons that correspond to that peak, because they were directly proportional to that number. Here, peak areas and the whole concept of integration is irrelevant in carbon-13, because the peaks are not proportional to the number of carbons. Finally, so if you see a carbon-13 spectrum, you will see oftentimes different peak heights. They really don't mean anything. So don't overinterpret them, because you might get into trouble. Finally, the last piece of information is the spin-spin coupling. We've seen that the spin-spin coupling is a quite useful component of interpretation of hydrogen-hydrogen spectrum, and the spin-spin coupling is common. In carbon-13, spin-spin coupling is actually fairly rare, because it would require that we have 2 carbon-13s in the same molecule immediately adjacent to each other, which is a very unlikely situation given the low natural abundance of carbon-13. So this we will never observe. But what we might be observe is coupling between 2 nuclei. So this is the so-called heteronuclear coupling between carbon and proton, and in principle this should be observable. However, we intentionally suppress this. And this is suppressed through continuous irradiation of protons while collecting the carbon NMR spectrum. This continuous radiation keeps all protons in their beta state, their high energy state, which then prevents them from splitting the peaks of the carbon, since there are no alpha and beta orientations to split. And so, again, another thing that comes out of this is that all peaks are singlets in carbon-13 NMR spectrum. This phenomenon is suppressed in carbon-13 NMR spectra because the complexity of spectra would probably be overwhelming. Since each carbon would couple with each proton on top of the proton coupling we see already, which would then cause a lot of difficulties in interpretation. So it turns out that in combination with proton spectra, decoupled carbon spectra, even though the all peaks are singlets, still give us enough information to resolve the structure of the most complex molecules. And in the next subtopic we will see how do we actually do this.